I'm here and super excited to be here again. I've actually have had a chance to meet some of you previously because, as Brett mentioned, my husband's an alumnus of William & Marion, so I've been able to go to some of the parties at AGU, and so I've been able to meet some of you. But if I haven't had the chance, I'm a planetary geologist, and in most of my research, I use the sedimentary record to interpret past and present environments on planetary bodies as a way to constrain their climate, hydrology, and potential for habitability. And most recently, this research has focused on Earth and Mars, although I've also been dipping my toes on moon research as well. I also conduct analog studies in Earth's polar regions to help characterize icy environments possibly present on early Mars and also during Earth glaciations. And so, for example, this is a picture of me here on the right, arriving in Antarctica back in 2015 on my way to study frozen lakes in the McMurdo Dry Valleys. And so my research and the tools that I use are very interdisciplinary and diverse. I commonly integrate field-based and underwater studies with remote sensing and numerical methods. Also, as Brett mentioned, I'm going to be starting a faculty position in January 2021. And so I am recruiting students to join my group. And so if anything that I will be talking about today is of interest and you're looking into going to grad school, feel free to email me. Also, my husband, Carl Lang, who's also starting, is looking for students. And so please contact him if you're interested. His focus is mostly on thermochronology and tectonic geomorphology. In addition to research, I'm also involved in a variety of organizations helping to increase the representation of Latinx in the geosciences, but also providing a support network for us to come together. And so these organizations include SOLES, which is the Society of Latinx, Hispanic, Earth, and Space Scientists. There's also a GeoLatinas, which is an international group of Latinas in the geo and planetary sciences. And you might have heard of GeoLatinas. We're quite active on social media, so please check that out. And then also the Boricua Planeteers, which is a group of Puerto Rican space and planetary scientists. And as Brett mentioned earlier, I myself am from Puerto Rico. And so all of these organizations do have an online presence. And so if you're interested, or if you know somebody who may be interested in finding out more about these, please give them my email, and I'll be happy to talk to them. And we're always recruiting, so please spread the word. All right, so enough about me. Today, as the title of my talk suggests, I'll be talking about reconstructing ancient environments on Mars using data at the grain size to the landscape scale. For most of my talk, I'll be focusing on interpreting depositional environments on Mars with the Curiosity rover using a grain size proxy that I developed. And then for the last 10 or 15 minutes or so of my talk, I will focus on some of my more recent work mapping deltas on Mars to revisit this idea that Mars had a global ocean. All right, so for both parts of my talk, my research is focused on a location that's called Gale Crater, or the Gale Crater region of Mars. Gale is the home of the Curiosity rover. It's a crater that's located in the equatorial regions of Mars, shown here on the left. On the right is a black and white image of Gale Crater with its central mound highlighted called Mount Sharp. And the star is where Curiosity landed. Gale straddles what we call the dichotomy boundary of Mars. It's probably one of the most striking features of the red planet. It's the boundary that separates the smooth northern lowlands from the rough southern highlands, and Gale crater is sort of right smack in the middle of that. And there's geologic evidence that water flowed from the south towards the north and pooled locally in Gale crater in the surrounding regions, either in lakes or possibly a northern ocean. Based on crater counting, Gale crater formed about the time when the climate of Mars was changing from one that was wet and potentially warm to mostly the cold and dry conditions of today. During this time, the mineralogy of alteration, or the composition of alteration minerals, was also changing from what we call clays to sulfates. And this sort of transition in mineralogy is something that we see in the lower reaches or lower strata of that central mound in Gale crater. And so it's possible that the environments that are preserved in Gale crater sort of record this climatic change on Mars from wet to dry conditions. From a habitability standpoint, Gale crater is an attractive place to study because lakes likely formed in Gale, and lakes could have provided a stable habitable environment for life to have evolved. And we also know from Earth that lake deposits, in particular mud, is good at preserving biosignatures. And so with that, in Gale crater, we can address two of NASA's main goals for exploring Mars, which are to follow the water and explore habitability. And so, and this is sort of shown here on this left schematic with the Curiosity rover right here, as I said, sort of achieving these two goals. The more recent rover that we're sending to Mars, called Perseverance, ticks off all three of these goals, since it's also looking for signs for biosignatures. And while I'm not going to be talking about Perseverance, if anybody has questions about that, I'll be happy to answer that at the end. So combine the climatic, hydrologic, and habitability history preserved in Gale crater is one of the reasons that Curiosity was sent there, and also why I find this region to be really interesting. And so for today, my talk is gonna focus more on the hydrologic part of this story, specifically addressing two questions. For the first part of my talk, I will address what environments are preserved in the sedimentary rocks in Gale crater, and what does this imply about Mars's paleohydrology. And then for the second part, I want to know how much water was sustained in the broader Gale crater region, and from geomorphology, and can we use that to distinguish whether there were multiple lakes or a global ocean. So to address the first question, I'll be using data from the Curiosity rover, which is shown here. And I just wanted to mention that because I will be showing data from the Curiosity rover, this is a very collaborative mission. There are hundreds of people involved in this mission. And so while I will be talking about my personal investigations, there are hundreds of people that have sort of helped bring this in together. All right, so the main goal of the Curiosity mission has been to, or one of the main goals of the Curiosity mission has been to characterize habitable environments on Mars from the sedimentary record in Gale crater. Since landing, the Curiosity rover has actually traversed approximately 23 kilometers, which is about 18 miles towards the lower reaches of Mount Sharp, which is its final destination. And so here on the left is that black and white image of Gale crater with the landing site, the star highlighting the landing site. And then on the right is a blown up sort of portion of that. And the yellow is sort of where the rover has been traversing, and it's going up Mount Sharp. And so Mount Sharp, again, is that central mound in the middle. And so this is sort of the lower reaches of that here on the bottom. And so along the way, along this traverse, we've actually found sedimentary rocks that show clear evidence for the transport of grains by liquid water. And since water is essential for life as we know it here on Earth, we would like to know what wet or aqueous environments were present when these grains were transported, and for how long they were present. One way that we can determine the depositional environments preserved in Gale crater is to interpret the transport energy from the grain size of sediments in these rocks. And this is why I think sediments are super cool. Anybody who's been to a marsh or a tidal environment at a beach may have seen a lot of fine sediments like mud and sand, for example, shown here on the left. Whereas if you were to go to a mountain stream, those are more likely to have coarser sediments like cobbles and boulders. And so in general, sediment grain size reflects their transport energy, and that's because it requires more energy to transport larger grains, which is why mountain rivers tend to have coarser sediments than quiet tidal environments. And so in the sedimentary record or rock record, these depositional environments are preserved in sedimentary rocks. And so the mud and sand from these tidal flats would be preserved as layers of mudstones and sandstones, whereas the river cobbles shown here, for example, could be preserved in conglomerates. And so by looking at the size of grains in these rocks, we can reconstruct their depositional environment, along with other sedimentary textures, of course. On Earth, I'm sure you've all have done this. It's quite easy to go in the field with a hen lens and a grain size card, like this one on the left. You could just, smack that grain size card next to a rock and get at grain size quite easily. However, we can't really do that on Mars. And so for Martian rocks, we use images. And so Curiosity actually has 17 cameras, and we use the images from these cameras to characterize the outcrops that we encounter. The main camera that we use to do this is called the MAHLI, which stands for the Mars Hand Lens Imager, which can resolve grains that are about coarse silt in size, and so around 60 microns. And you actually can't see MAHLI in this picture because MAHLI is on the rover arm, and we use MAHLI to take the rover selfies. And so it looks like it's not in the image, but you can actually see the shadow of the arm. That's just an effect from how we stitch together all the selfie images, which I think is cool. So next time you see a Curiosity selfie, go and check out to see if you can actually find the shadow of the arm. All right. So in general, coarse grains are well resolved in Curiosity images. For example, here on the left is a coarse sandstone, and on the right is a conglomerate, and both of these rocks are rocks on Mars. And in both cases, we can actually see individual grains. For example, there's this beautiful translucent grain here on the left, and this sub-rounded pebble here on the right. However, while coarser grains are well resolved, finer grains are harder to resolve in Curiosity images. For example, this mudstone and fine sandstone, where we really can't resolve grains, even with the highest resolution images that we have. And that's not only due to the limitations of the camera, but also due to the distance to the rocks, and also dust cover. Mars is really dusty, and the dust is everywhere, and it really makes it difficult to resolve grains. And so this is actually a problem. Not being able to distinguish between mud and sand sort of troubles sedimentologists. And that's because this transition distinguishes transport of grains, typically distinguishing the transport of grains in suspension versus traction. And this is information that we need to be able to constrain a depositional environment. Moreover, as I mentioned, lake muds, and so mudstones, are commonly associated with lake environments, and because lakes are a major target for the Curiosity mission, it's really important for us to be able to positively identify mudstones. And so to complement grain sizes using images, I developed a technique that uses geochemical data from the ChemCam instrument on the rover to interpret grain size in rocks. So ChemCam, it's an instrument suite. It consists of a laser-induced breakdown spectrometer and a camera that provides context images for the LIBS measurements. And so the LIBS, so again, the laser-induced breakdown spectroscopy technique, uses a pulsed laser originating from the rover eye, the rover head. And so it uses that pulse laser to sort of vaporize small spots that are 2 to 7 meters away from the rover. And it's the light that's produced from the plasma during that process that we measure to get at the composition of rocks. And so here on the right is an example of some of these ChemCam laser marks on a rock on Mars, showing how we typically sample rocks. And so we typically use this matrix, we typically sample using a matrix or in lines. The reason I'm able to connect grain size with the ChemCam data is because we do know the approximate size of where the laser hits, which varies between medium to coarse sand in size. And so what this means is that if a rock has grains considerably smaller than that, say a mudstone, for example, then what we measure is the bulk rock composition at each of those LIBS points. And so we expect to see low point-to-point chemical variability because it's just bulk rock composition at each point. However, if a rock has grains that are larger than that, for example, about the size of that laser spot, like in a sandstone, then it's possible that we might be able to get chemical contributions from individual grains at each point. And so we would expect high point-to-point chemical variability. And of course, this only works if the sand grains have diverse compositions, which we do know is the case for rocks analyzed by Curiosity, because ChemCam does provide us with chemical information. And we also have other instruments on the rover that provide us information about chemistry. And so kind of like a grain size card, I'm able to systematically infer or interpret grain size for rocks on Mars by quantifying the compositional variability between LIBS points. And I do that by using a statistical parameter called the Gini index, which varies between 0 and 1, where 0 means no point-to-point variability and 1 means completely heterogeneous. For today's talk, low Gini indices means finer grain sizes, and higher Gini indices mean coarser grain sizes. Due to time, I can't go into the specifics of the quantification, but if you're interested, I do have a paper going through all the nitty-gritty details about the technique. And of course, I'm happy to answer any questions that you may have. So I've been using this technique to estimate rock grain size along Curiosity's traverse. And today I'm going to be showing some example data and interpretations for what we call the Murray Formation, which the rover entered at a site called Pahrump Hills. And so here on the left is, again, that black and white image of Gale crater, highlighting sort of the rover traverse here on the right. And so Pahrump Hills is here on the red, and so this is where we entered the Murray Formation. And then the green is showing the aerial extent of that. And my little rover dudette is showing the current location of the rover for context. The most detailed sedimentological study that we've done so far has been in Pahrump Hills, because it is when we first entered the Murray Formation. And from that one location and from images, we know that it consists of mudstones interbedded with sandstones, and these were interpreted as reflecting the deposition of sediments from streams originating from the crater rim into a lake in the middle, as shown here on the bottom right. These are some examples of some of these rocks. Here on the left is this beautiful image of these laminated mudstones, which are the lake deposits from Pahrump Hills. And then on the right are these beautiful cross-bedded sandstones, which are the river deposits. And so outside of Pahrump Hills, we've also identified mudstones and sandstones with images in the rest of the Murray, which is about 300 meters thick. This is shown here on the right. And so this is a stratigraphic column, which is a graphical representation of grain size versus elevation. And just note that these are negative, but going up is higher in elevation. And so here in the grays are mudstones, yellows are sandstones, and then the browns are a location where we have both lithologies, and it's a location where we actually see quite rapid grain size changes. And so the distance between sandstones and mudstones are smaller than the frequency that we take images. And so a lot of my research really has focused on using the Gini index technique to sort of fill in the grain size information for where we don't have images along the traverse. And the reason I've been able to do that is because ChemCam measurements are taken more frequently than images. And so that's allowed me to produce an almost continuous record of grain size along Curiosity's traverse. All right, so to be able to use the Gini index to get a grain size, I first had to calibrate it to rocks with known grain size. And so here are some examples of some of these calibration rocks. On the left is a fine grain sandstone, and I know its Gini index. And on the right is a medium grain sandstone. Maybe you can clearly see grains, and I know its Gini index. And so by connecting the grain size of these and other rocks in the Murray to their Gini index, I've been able to develop a grain size scale, which is shown here. And so this is a plot of Gini index versus grain size determined from images for individual rocks. And so each point here is data for an individual rock. And again, I know its grain size from images, and I know its Gini index. And as expected, rocks that are coarser have higher Gini indices. And the distribution of grain size with the Gini index is quite sort of limited or constrained in a way that I'm able to, as I mentioned, develop a grain size scale just based off the Gini index numbers. And so with this scale, I've been able to interpret grain size for other rocks in the Murray Formation, which is what I'm going to be showing you today. And so I'm actually going to be showing you data that spans for 4 years and 300 meters of stratigraphy in the Murray. All right, so this is what the data looks like. On the left is the full stratigraphic column for the Murray that I showed previously. And on the right is a plot of Gini index versus elevation, where each individual point is a rock. And so here are essentially data for 371 rocks in the Murray Formation, with the grain size scale that I showed previously sort of overlaying on top of that. And so based on this, we can see that most of the Murray is dominated by mudstones. We can see this more clearly in a histogram where most of the rocks are dominated by mud, but we also see that there are coarser rocks, which is interesting. Based on what we know from images, the fact that we have rocks that are predominantly mud, and from the textures that we see from images, we interpret this to suggest that these sediments were deposited predominantly in quiet conditions, most likely a lake. Some of the mudstones in my analyses also have sedimentary structures that look like mud cracks in images. And so this is just an example of one of these rocks. And so this is actually the first evidence that we have for mud cracks on another planet. And so this is a really cool image. So here on the left is sort of a close-up on that, showing again these beautiful mud cracks. And the colored lines are where my analyses were from. And so my data has been able to sort of help confirm that these rocks are indeed dominated by mud-sized grains. And so the presence of these mud cracks are important because they suggest that there were water level changes in this lake or lakes in the past with drying conditions. In addition to laminated mudstones and the mud cracks, there are also some mudstones that are sandy. And so here on the left is an example. So this is a sandy mudstones, and sandy mudstones are actually characteristic deposits of seasonal and perennially ice-covered lakes, which suggests that this ancient lake in Gale possibly experienced local climate changes. Although I should note that these sandy mudstones were only observed in one location throughout the 300 meters. And so we really don't see any other evidence for icy or cold conditions in the rest of the Murray. And the reason I talked about this is because I of course, do research in frozen lakes. And so if you have any questions about this, I'm more than happy to answer that. All right, in addition to the mudstones, there are also coarser rocks. In particular, there's one stratigraphic horizon where we see this beautiful trend of coarser rocks that are associated with what we call trough cross-bedded sandstones. And these are unique because they require a rapid fluid flow to form. And on Earth, these occur either due to the wind or by streams. And so these are essentially preserved dune deposits. And so this suggests that in addition to the lakes and the drying conditions, there are also higher energy depositional environments present on Mars. All right, so I'm going to walk you through part of this section just to show you some of the diversity in the grain sizes that we see in the Murray. And we're going to start around here where we go from a location that's dominated by mudstones into a horizon where we see those mud cracks and laminated mudstones and also some sandstones, back into an area predominantly with mudstones, into those beautifully trough cross-bedded sandstones, back to a region stratigraphically that has mudstones. And so again, based on what we know from images, an interpretation would be that we had a lake that had drying conditions, and a later point in time, that lake either refilled or there was a completely new lake. And then we had a period where we had dunes, either from inflowing streams or by the wind, back to a period where there was a lake. This variability suggests that Mars had an active hydrologic cycle. Potentially, there would have been streams originating from the crater rim flowing into a lake in the center of the crater, and that lake was experiencing water level changes to be able to explain the mud cracks. And this lake, or lakes, predominantly experienced open water conditions, and that's due to the fact that we lack any evidence for ice-related deposits. Although, as I mentioned, we do have a stratigraphic horizon with sandy mudstones, which suggest at least temporary icy conditions associated with either a seasonally ice-covered lake or perennially ice-covered lake, suggesting that there were local climate changes in Gale crater. All right, and then I should mention that you know, if all of these environments get eroded down, then Curiosity is sort of roving through the remnants of all of those environments. And so this is just a schematic showing those relationships. All right, so going back to the first question, what environments are preserved in the sedimentary rocks in Gale crater, and what does this imply about Mars's paleohydrology? As I just showed, we have clear evidence for lakes, rivers, mudflats, and maybe dunes from either formed by wind or by rivers, which suggests that Mars had an active hydrologic cycle with potential changes in local climate, and the general absence of perennially ice-covered lake deposits and also other icy features such as sand wedges, which are associated with patterned ground, suggests that the climate when these lakes formed was predominantly warm and wet. And then using sedimentation rates for lakes on Earth, and also knowing that we have about 300 meters worth of predominantly lake deposits, we can make an estimation that the lake or lakes were sustained for tens of thousands to millions of years, which maybe for Earth geologists seems like a big stretch, but for us Martians, it's one of the best constraints that we have for lake deposition. This is sort of the end of part one. I'd be happy to take questions about this part, or I can continue. I don't know how everybody is feeling. I'm gonna take the silence to suggest I should continue.
We're all gonna be too shy to speak up.
Okay. All right. So I'm gonna be transitioning down now from the grain size to more of the landscape scale. In particular, I'm gonna be addressing the part two of my open questions, which is from geomorphology, how much water was sustained in the broader Gale crater region, and was that in multiple lakes or a global ocean? And I should mention that this is work that I've been doing as a postdoc at Dartmouth College, and also working with an undergrad named Melanie Canning. And so this work, as the work previously, is also collaborative. All right, so this is an example of a delta in the Gale crater region, and this is an actual image. This is not a drawing or anything like that. And so we can see that the delta emerges from an incised valley and has this beautiful arcuate shape with a stipply dipping front, which is characteristic of deltas. And deltas form in standing bodies of water. And on Earth, they generally form in lakes and in oceans. And so these are two examples of terrestrial deltas. The two on the left are from a lake in China, and then on the right is an example from a delta in Greenland. And in all these cases, you can see that these deltas have, again, this beautiful arcuate shape, and that they also emerge from these incised valleys where they're streams. The paleohydrology of these bodies of water can be reconstructed by using the elevation of the front of the deltas. And so this is what's highlighted here in blue. And that's because these are a proxy for stable paleo water levels. And so this is where the water level was stable when the delta formed. And so using these really basic concepts, a global delta study of Mars interpreted that deltas that formed along this dichotomy boundary of Mars formed in a northern global ocean. And so this is a topographic map of Mars, and the diamonds are the locations of the deltas that were used to reconstruct this paleo shoreline, which is in magenta, which sort of follows what we call the dichotomy boundary of Mars, and has been interpreted to sort of represent the shoreline of a northern ocean. This global study actually included 2 deltas within Gale crater and another 8 deltas in the broader Gale crater region. And interestingly, at least for Gale crater, there really isn't any geomorphic evidence suggesting that these deltas were ever part of a global ocean. Instead, the data suggests that deltas in Gale crater likely formed in lakes. And so in addition to the lake deposits recorded in the sedimentary rocks that I was just talking about, from the geomorphology, there's evidence that lakes formed at a later point in time. And so these are younger lakes. And so here on the left is Gale crater, and the closed contours here are sort of reconstructions of the paleo water level for the lakes that we think formed in Gale crater. Here in the blue are the locations of deltas, and there's also alluvial fans in Gale crater that are associated with these potential lakes. And on the right is an example of one of these deltas. This is a beautiful image. This is what we call the pancake delta, which sort of looks like a pancake. So because of sort of this new data, this really challenges the idea that the other dichotomy deltas formed in a global ocean and that maybe they also formed in lakes. And this actually may have huge implications as the Gale crater region has the highest concentration of these dichotomy deltas, and deltas are actually the strongest evidence that we have for this northern global ocean. And so a natural question would be, do the deltas in the Gale crater region record a global ocean? And so do the other deltas in this region, did they form in lakes or in an ocean? And so to address this question, I've analyzed new and previously identified deltas with updated imagery and derived topography. And this included digital elevation models that I made that were 6 meters per pixel in resolution. I also used a blended digital elevation model at a higher resolution that had global coverage at 200 meters per pixel resolution. And then also nighttime thermal infrared images. And that's because deltas and other landforms really pop out in thermal infrared images than they do in visual images. And so it really helped me with some of the mapping in this project. For my inventory, I classified landforms as either deltas or alluvial fans. Deltas, as I previously mentioned, have this beautiful, at least on Mars, they have this beautiful arcuate form with low gradient tops and steeply dipping fronts. And so here on the right is a transect on this delta here on the left, showing just that, showing this the steeply dipping front, which again, we can use as a proxy for paleo water level. And on the right is an example of an alluvial fan on Mars, again, with a transect from B to B prime, showing that alluvial fans tend to have more concave up to linear long profiles. And so by using these differences, I was able to map landforms in this region. All right, so zooming into the Gale crater region, this is again the topographic map of Mars. On the diamonds here are the original deltas identified by this previous study that I was mentioning. Now on top of that are the new landforms that I identified in my study. The diamonds are landforms that I interpreted as deltas, and then the triangles are landforms that I interpreted as alluvial fans. And one of the things that immediately pops out is the high number of these landforms in this region. It's completely littered with them, but also that a lot of these landforms occur in clusters. And so showing this data in sort of plot form. So this is a plot of the elevation of those delta fronts versus longitude. And again, one of the things that we see is that these deltas are commonly clustered geographically. And the deltas that are sort of clustered together, they tend to have very similar delta front elevations. And so some of these groups are highlighted here in circles. And the blue line here is the water level from that hypothesized global ocean from that previous study for context. And so using this information, we interpret that the deltas that are in the same region and have these same front elevations formed in the same same standing bodies of water. And so by averaging so these essentially formed in different bodies of water, all these little groups. And so by averaging the front elevations of the deltas in each of these groups, what we found was evidence for 10 different paleo lakes, and 4 of these lakes hosted multiple deltas. And the largest would be a little bit smaller than Lake Ontario, just to give you a reference. And so together, these 4 lakes could have stored approximately 5 centimeters global water equivalent. And so this is sort of the depth of water if we were to spread it out equally on Mars. That's, again, how thick that would be, which would be 5 centimeters, which is actually not a lot. Previous estimates for that inferred ocean that I was talking about is 550 meters. And so the amount of water is considerably less if these deltas formed in these lakes. The presence of these lakes has also been supported by initial geomorphic analyses. And this is a work that Melanie Canine did working with me. She was an undergraduate at Dartmouth, soon to be a grad student at Caltech. And she observed that the basins, and again, I should mention that she did this work completely independent from me. I just sort of gave her the location and she did her own mapping. And from her work, she found that basins tend to have really smooth textures in the middle compared to surrounding topography. And she also found evidence for possible shorelines. And so here on the right is an example of some of these possible shorelines. And so she really independently mapped one of these basins, sort of helping support my interpretations from the work that I've been doing with the deltas. And so one of our interests is to sort of do this sort of analysis in some of the other regions in the region, in the broader region. All right, so going back to the original question that I had, did the deltas in the Gale crater region record a global ocean? Short answer is no. It looks like the deltas likely formed in several paleo lakes. However, we can't rule out that there was a northern global ocean, and that's because there are other features that are inferred to form in an ocean. Although all of these are very controversial. These include what we call valley networks. There are paleo features that people interpret to be paleo shorelines, although recent work has really shown that these aren't paleo shorelines. And then there are other dichotomy deltas apart from the ones that I showed. The next question is, some people have asked me, are these lakes in the Gale region, are they remnants, could they be remnants of an ocean during a later waning stage? And the short answer again is that it's quite unlikely. We don't really have any evidence for progradation. And so if there was a larger body of water and the deltas were forming into that body of water and the water dropped, the front of the deltas would have changed with that changing water level, and we don't see that at all in any of the deltas. And so again, it seems unlikely that these are remnants. However, we do see that some of the deltas are overlain by alluvial fans, and so it looks like the deltas sort of formed into whatever standing body of water they were forming in, and then at a later point in time, alluvial fans sort of formed on top of that, which suggests that there were climate changes, likely from wet to dry conditions, as alluvial fans need considerably less water to form than deltas. All right, so to answer the second question of my talk, from geomorphology, how much water was sustained in the broader Gale crater region? Was it in multiple lakes or a global ocean? As I just showed very quickly, the deltas in this region record multiple paleo lakes and not an ocean. And if we were to add all of that water together from all of those paleo lakes, they could have sustained at one point in time 5 centimeters of global water equivalent compared to the 550 meters from, if the deltas formed in a northern global ocean. And so with that, I'm going to put both of the questions up again and then take any questions.